Erosion or erosion-corrosion damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of erosion or erosion-corrosion based on API 571. The first is erosion is the accelerated mechanical removal of surface material as a result of relative movement between, or impact from solids, liquids, vapor or any combination thereof. The second is erosion-corrosion is a description for the damage that occurs when corrosion contributes to erosion by removing protective films or scales, or by exposing the metal surface to further corrosion under the combined action of erosion and corrosion. Erosion or erosion-corrosion damage, a description in terms of mechanical and metallurgical failure mechanisms. Erosion-corrosion is a complex degradation process that combines the mechanical wearing away of material, or erosion, with chemical or electrochemical reactions, corrosion, that lead to material failure. Understanding these mechanisms requires a multidisciplinary approach that includes both mechanical and metallurgical principles. Description of erosion or erosion-corrosion in terms of mechanical failure mechanisms point of view. Number 1 is mechanical, where erosion typically occurs due to surface interactions with solid particles, liquids, or gases that are in motion. The mechanical impact and friction of these particles can lead to the removal of material from the surface, analogous to abrasive wear. This process can be accelerated in environments where high fluid velocities, turbulence, or impacts from particulates are present. Number 2 is failure modes. Mechanical failure can manifest in several ways, including: the first is material loss. Continuous exposure to erosive agents leads to gradual thinning of the material, ultimately compromising structural integrity. The second is pitting and grooving. Repeated impacts may create localized indentations, pitting, or channels, grooves, on the surface, which aggravate the corrosion process by exposing fresh material to corrosive reactants. The third is surface fractures and cracking. Stress concentrations due to material loss can initiate cracks that propagate under cyclic loading or in the presence of corrosive environments. Number 3 of mechanical failure mechanisms of erosion or erosion-corrosion is fatigue mechanisms, include: the first is the cyclic nature of erosion can introduce fatigue stresses, especially in materials subjected to dynamic loading. Material fatigue can lead to premature failure even if the material has a high resistance to corrosion or wear when considered separately. The second is fluctuating loads. Components subjected to alternating stresses during operation can be susceptible to fatigue failure exacerbated by erosion. The cumulative effect of erosion on the critical stress points can lead to premature failure. Number 4 of mechanical failure mechanisms of erosion or erosion-corrosion is flow dynamics. The characteristics of fluid flow, including turbulence and velocity gradients, significantly influence the severity of erosion. Unfavorable flow patterns can enhance erosion rates by leading to local stagnation or reentrant flows where debris accumulates and exacerbates wear. Description of erosion or erosion-corrosion in terms of metallurgical failure mechanisms point of view. Number 1 is surface degradation. Erosion leads to the breakdown of the protective oxide layer that often forms on metal surfaces. Reduced protection accelerates corrosion processes, particularly in aggressive environments, applying a synergistic effect where erosion and corrosion reinforce each other's severity. Number 2 is electrochemical reactions. In environments where erosion occurs in the presence of corrosive media, electrochemical corrosion can significantly contribute to material degradation. This can include: the first is anodic dissolution, the active removal of metal ions from the surface due to electrochemical reactions exacerbated by mechanical erosion. The second is localized corrosion. Erosion can lead to preferential sites for corrosion, resulting in localized damage such as pitting corrosion, where material loss is concentrated in small areas. Number 3 is cathodic and anodic areas. Erosion-corrosion can create differential areas on the metal surface, leading to anodic, more corroded, and cathodic, less corroded, regions. The localized nature of corrosion processes can result in uneven wear and localized thinning of the component, increasing the risk of leakage or rupture. Number 4 is microstructural changes. erosion-corrosion can lead to changes in the microstructure of materials, such as: the first is phase transformation. Certain materials may undergo undesirable phase changes under mechanical and thermal stress, altering their corrosion resistance. The second is grain boundary degradation. Continuous material loss can expose grain boundaries, which are often more susceptible to corrosion processes, leading to intergranular attack. Number 5 is stress corrosion cracking, or SCC. The combination of tensile stress, corrosive environments, and surface defects initiated by erosion can contribute to SCC. This type of failure is particularly dangerous as it can lead to unexpected and catastrophic failures. Number 6 is passivation breakdown. Some materials form protective oxide layers that inhibit corrosion. Mechanical erosion can disrupt these layers, making the underlying metal more susceptible to environmental attack. The breakdown of passivation films can lead to rapid material loss. Number 7 is influence of alloy composition. The resistance to erosion-corrosion is highly dependent on the alloy's composition, which can affect both mechanical and electrochemical properties. For example, the addition of certain alloying elements can enhance corrosion resistance but may decrease toughness, making the material more prone to cracking under erosive conditions. Erosion-corrosion damage exemplifies the interaction between mechanical and metallurgical failure mechanisms. The combined effects of mechanical wear and electrochemical degradation necessitate a comprehensive understanding to effectively predict, prevent, and mitigate material failures in engineering applications. A thorough approach must take into consideration the specifics of the environment, material properties, and operational conditions to devise appropriate strategies for material selection, design, and protection against erosion-corrosion. Erosion or erosion-corrosion damage mechanisms affected materials based on API 571, all metals, alloys and refractories. Erosion and erosion-corrosion are processes that can damage materials through mechanical and metallurgical failure mechanisms. These mechanisms can affect a wide range of materials, especially metals, polymers, and ceramics, and understanding them is essential in industries such as oil and gas, chemical processing, marine engineering, and power generation. Here's a breakdown of the erosion or erosion-corrosion affected materials and the associated failure mechanisms. From affected materials' point of view, we can break down them as following. Number 1 is metals. The first of metal is carbon steels, commonly affected due to their susceptibility to both erosion and corrosion. The second of metal is stainless steels. While they have good corrosion resistance, they can still suffer erosion-corrosion in certain environments. The third of metal is nickel alloys, often used in harsh environments, but can still be vulnerable to erosion when subjected to flowing media. The fourth of metal is aluminum alloys, can corrode easily when pitted or eroded, especially in marine conditions. The fifth of metal is titanium alloys, exhibits good corrosion resistance but can still face erosion in aggressive environments. Number 2 of erosion or erosion-corrosion affected materials is polymers, include. The first is thermoplastics, can erode when exposed to high-velocity fluids or mechanical impacts, commonly used in piping and linings. The second is elastomers, used in seals and gaskets. Erosion due to wear can lead to loss of function. Number 3 of erosion or erosion-corrosion affected materials is ceramics, include. The first is traditional ceramics, such as, porcelain can fail under mechanical stresses caused by erosive particles in service conditions. The second is advanced ceramics, often used in environments prone to erosion, but can be brittle and susceptible to cracking. Affected materials of erosion and erosion-corrosion from mechanical failure mechanisms point of view, we can break down them as following. Number 1 is abrasive erosion, include. The first is mechanical wear due to the impact of solid particles or abrasive materials. The second is material is removed in small quantities, leading to surface roughness and eventual penetration. Number 2 of erosion or erosion-corrosion affected materials from mechanical failure mechanisms point of view is cavitation, include. The first is formation and collapse of vapor bubbles in a fluid, leading to shock waves that can damage materials. The second is common in pumps, turbines, and propellers, resulting in surface pitting and material loss. Number 3 of erosion or erosion-corrosion affected materials from mechanical failure mechanisms point of view is impact damage, include. The first occurs when solid particles strike a surface at high velocity, leading to localized deformation or cracking. The second can lead to the initiation of fatigue cracks. Number 4 of erosion or erosion-corrosion affected materials from mechanical failure mechanisms point of view is fatigue failures. Fatigue failures is where repeated erosive impacts can cause fatigue cracking over time. Affected materials of erosion and erosion-corrosion from metallurgical failure mechanisms point of view, we can break down them as following. Number 1 is corrosion. In the presence of moisture or corrosive agents, metals can undergo electrochemical reactions, leading to material loss. Erosion can exacerbate corrosion by removing protective oxide layers or creating sites for corrosion initiation. Number 2 is pitting corrosion, localized corrosion leading to small pits, which can be accelerated by erosive wear. Particularly problematic in stainless steels. Number 3 is galvanic corrosion, occurs when two different metals are in electrical contact in a corrosive environment, accelerated by erosion processes. Number 4 is stress corrosion cracking, SCC, a combination of tensile stress and corrosive environment that can lead to suddenly catastrophic failures. Number 5 is intergranular corrosion, corrosion that occurs along grain boundaries in polycrystalline materials, often exacerbated by erosion processes. Understanding these materials and their failure mechanisms is crucial for selecting appropriate materials and designing systems that can withstand erosive and corrosive environments, ultimately helping to enhance the durability and reliability of engineering systems. Erosion and erosion-corrosion based on API 571, the first is in most cases, corrosion plays some role so that pure erosion, sometimes referred to as abrasive wear, is rare. It is critical to consider the role that corrosion contributes. The second is metal loss rates depend on the velocity and concentration of impacting medium, such as particles, liquids, droplets, slurries, two-phase flow, the size and hardness of impacting particles, the hardness and corrosion resistance of material subject to erosion, and the angle of impact. The third is softer alloys such as copper and aluminum alloys that are easily worn from mechanical damage may be subject to severe metal loss under high-velocity conditions. The fourth is although increasing hardness of the metal substrate is a common approach to minimize damage, it is not always a good indicator of improved resistance to erosion, particularly where corrosion plays a significant role. The fifth is for each environment material combination, there is often a threshold velocity above which impacting objects may produce metal loss. Increasing velocities above this threshold result in an increase in metal loss rate. This table illustrates the relative susceptibility of a variety of metals and alloys to erosion/corrosion by seawater at different velocities. The sixth is the size, shape, density and hardness of the impacting medium affect the metal loss rate. The seventh is increasing the corrosivity of the environment may reduce the stability of protective surface films and increase the susceptibility to metal loss. Metal may be removed from the surface as dissolved ions, or as solid corrosion products which are mechanically swept from the metal surface. The eighth is factors which contribute to an increase in corrosivity of the environment, such as temperature, pH, etc., can increase susceptibility to metal loss. Erosion and erosion-corrosion are significant issues in various industrial applications, particularly in the oil and gas, power generation, and chemical processing industries. Understanding the critical factors that contribute to these forms of damage involves several mechanical and metallurgical failure mechanisms. Several critical factors influence this damage mechanism. Number 1 is mechanical factors, include. The first is fluid velocity. High fluid velocities can increase the impact of particles or fluid on surfaces, which accelerates erosion. The second is particle size and shape. The size, shape, and hardness of solid particles in the fluid can significantly impact the rate of erosion. Sharp-edged and harder particles tend to cause more damage. The third is flow patterns. Turbulent flow patterns can enhance erosion, as they can cause more frequent impacts on the material surface due to swirling and vortex formations. The fourth is impact angle. The angle at which particles strike a surface can determine the extent of damage. Typically, erosion is more severe at acute angles compared to obtuse angles. The fifth is surface roughness. Rough or irregular surfaces can trap particles and increase localized erosion. Smooth surfaces may experience less erosion but can still be affected by corrosion. The sixth is mechanical stress. Existing mechanical stresses, like tensile stress, can exacerbate erosion and corrosion processes, leading to premature failure. The number 2 of several critical factors influence the erosion and erosion-corrosion damage mechanisms is metallurgical factors. The number 2 of several critical factors influence the erosion and erosion-corrosion damage mechanisms is metallurgical factors. The second is corrosion resistance. The inherent corrosion resistance of a material can significantly affect its overall degradation in erosive environments. Materials with poor corrosion resistance are more prone to erosion-corrosion interactions. The third is microstructural considerations. The microstructure of a material, such as grain size, phase distribution, can influence erosion and corrosion resistance. For instance, a finer microstructure may enhance resistance to crack propagation. The fourth is protective coatings. The presence and quality of protective coatings, such as paints or alloys, can provide a barrier against erosion and corrosion. However, if coatings are damaged, they may exacerbate degradation. The fifth is electrochemical factors. The presence of electrolytes in the fluid environment can enhance corrosion processes, particularly in the presence of erosion. Galvanic or concentration cell effects can occur, further accelerating material loss. The sixth is environmental factors. Conditions such as temperature, humidity, and chemical composition of the fluid can influence both corrosion rates and the susceptibility of materials to erosion. The number 3 of several critical factors influence the erosion and erosion-corrosion damage mechanism is failure mechanisms. The first of failure mechanisms is wear mechanisms, includes abrasion, which occurs when particles slide over a surface, and impact wear, which occurs due to high-velocity impacts. The second of failure mechanisms is corrosion mechanisms. Erosion-corrosion damage may involve localized attacks, including pitting and crevice corrosion, which occur more readily in dynamic environments. The third of failure mechanisms is fatigue crack initiation. Repeated impacts can lead to fatigue, causing cracks to initiate and propagate, leading to catastrophic failure. The fourth of failure mechanisms is intergranular corrosion. In some alloys, corrosion may occur preferentially along the grain boundaries, especially under stress or in the presence of certain environmental conditions. The fifth of failure mechanisms is cavitation. The formation and collapse of vapor bubbles in a fluid can create powerful shock waves that lead to significant material erosion, particularly in pumps and turbines. In summary, effective prevention and mitigation strategies for erosion and erosion-corrosion damage require a comprehensive understanding of these mechanical and metallurgical factors. Material selection, surface treatments, and operational adjustments can all play a critical role in extending the life of components subject to these forms of degradation. Erosion and erosion-corrosion damage mechanisms affected units or equipment based on API 571. The first is all types of equipment exposed to moving fluids and/or catalyst are subject to erosion and erosion-corrosion. This includes piping systems, particularly the bends, elbows, tees and reducers, piping systems downstream of let-down valves and block valves, pumps, blowers, propellers, impellers, agitators, agitated vessels, heat exchanger tubing, measuring device orifices, turbine blades, nozzles, ducts and vapor lines, scrapers, cutters, and wear plates. The second is erosion can be caused by gas-borne catalyst particles or by particles carried by a liquid such as a slurry. In refineries, this form of damage occurs as a result of catalyst movement in FCC reactor/regenerator systems in catalyst handling equipment, valves, cyclones, piping, reactors, and slurry piping, see Figure 4.43. Figure 4.43 is erosion-corrosion of a 1.25 cr 300 valve flange on an FCC catalyst withdrawal line. Equipment in both delayed and fluidized bed cokers, see Figure 4.44. Figure 4.44 is erosion of a 9 cr 1 mo coker heater return bend. And as we're on pumps, see Figure 4.45, compressors and other rotating equipment. Figure 4.45 is erosion-corrosion of his ASTM A48 Class 30 cast iron impeller in recycle water pump. The third is hydroprocessing reactor effluent piping may be subject to erosion-corrosion by ammonium bisulfide. The metal loss is dependent on several factors including the ammonium bisulfide concentration, velocity, and alloy corrosion resistance. The fourth is crude and vacuum unit piping in vessels exposed to naphthenic acids in some crude oils may suffer severe erosion-corrosion metal loss depending on the temperature, velocity, sulfur content and TAN level. Erosion and erosion-corrosion are significant mechanisms that can lead to mechanical and metallurgical failure in various units or pieces of equipment, particularly in industries such as oil and gas, chemical processing, and power generation. Here are some affected units or equipment along with the associated failure mechanisms. Affected units or equipment. Number 1 of affected units or equipment is pipelines, include, the first is impact. Erosion due to fluid turbulence, particulates, or corrosive agents can significantly reduce wall thickness. The second is failure mechanisms, wall thinning leading to leaks, structural failures due to loss of integrity. Number 2 of affected units or equipment pumps, include, the first is impact. Internal components such as impellers and volutes can experience wear from abrasive particles in the fluid. The second is failure mechanisms, impeller erosion, cavitation leading to pitting, fatigue and fracture due to alternating loads. Number 3 of affected units or equipment is heat exchangers, include, the first is impact. Erosion-corrosion can occur where turbulent flow or phase changes cause wear on tubes and plates. The second is failure mechanisms, loss of heat transfer efficiency, tube rupture, or leaks due to thinning. Number 4 of affected units or equipment is valves, include, the first is impact. Seats and bodies of valves may degrade due to the effects of high-velocity fluids and corrosive conditions. The second is failure mechanisms, valve seat erosion leading to leaks, failure of sealing surfaces. Number 5 of affected units or equipment is pressure vessels, include, the first is impact. Internal surfaces can suffer from combined erosion and corrosion from the materials handled. The second is failure mechanisms, thinning walls leading to potential ruptures or explosions, localized stress cracking. Number 6 of affected units or equipment is turbines, include, the first is impact. Blades and other components can erode due to high-velocity gas or liquids containing particulates. The second is failure mechanisms, loss of aerodynamic efficiency, blade failure due to fatigue or fracture. Number 7 of affected units or equipment is cooling towers and condensers, include, the first is impact. Water flow can cause corrosion and erosion of various materials when exposed to contaminants. The second is failure mechanisms, leakage, structural weakness leading to failure under load. Number 8 of affected units or equipment is storage tanks, include, the first is impact. Erosion from bottom corrosion or external factors can lead to significant integrity issues. The second is failure mechanisms, tank wall failure, potential spills leading to environmental hazards. Number 9 of affected units or equipment is marine structures, include, the first is impact. Offshore platforms or ships can experience severe erosion due to wave action and marine growth. The second is failure mechanisms, pitting corrosion, structural failure from reduced cross-section. Here are some affected units or equipment along with the associated failure mechanisms from mechanical failure mechanisms point of view, include. Number 1 is fatigue. Repeated stresses may lead to failure after significant material loss from erosion or corrosion. Number 2 is fracture. instantaneous failure can occur once the structural integrity reaches a critical point. Number 3 is brittle fracture, often associated with materials that have lost ductility due to corrosion or erosion processes. Here are some affected units or equipment along with the associated failure mechanisms from metallurgical failure mechanisms point of view, include. Number 1 is pitting corrosion, localized corrosion leading to small pits which can rapidly progress to failure. Number 2 is stress corrosion cracking, or SCC interaction between tensile stress and a corrosive environment leading to crack propagation. Number 3 is galvanic corrosion. Dissimilar metals in contact can accelerate corrosion processes, especially when eroded. Understanding the mechanisms and affected equipment helps engineers implement effective strategies to minimize risks and enhance the reliability of systems. The appearance or morphology of erosion and erosion-corrosion damage based on API 571. The first is erosion and erosion-corrosion are characterized by a localized loss in thickness in the form of pits, grooves, gullies, waves, rounded holes and valleys. These losses often exhibit a directional pattern. The second is failures can occur in a relatively short time. The appearance or morphology of erosion/erosion, corrosion damage can vary depending on the specific mechanical and metallurgical failure mechanisms involved. Here are some common characteristics of erosion and erosion-corrosion damage. Number 1 is mechanical failure mechanisms, include. The first is ductile erosion. Ductile erosion appears as a smooth, rounded, or wavy surface with a shiny or reflective finish. The material is removed by plastic deformation, and the surface may exhibit a flowed or stretched appearance. The second is brittle erosion. Brittle erosion appears as a rough, faceted, or pitted surface with a dull finish. The material is removed by brittle fracture, and the surface may exhibit a jagged or splintered appearance. The third is cavitation erosion. Cavitation erosion appears as a rough, pitted, or honeycombed surface with a dull finish. The material is removed by repeated implosions of vapor bubbles, and the surface may exhibit a Swiss cheese appearance. Here are some common characteristics of erosion and erosion-corrosion damage from metallurgical failure mechanisms point of view. The first is uniform corrosion. Uniform corrosion appears as a uniform thinning of the material, often with a smooth, matte finish. The second is pitting corrosion. Pitting corrosion appears as isolated, discrete pits or craters, often with a rough, irregular surface. The third is crevice corrosion. Crevice corrosion appears as a localized attack in areas where the material is shielded from the environment, such as under gaskets, bolts, or other components. The fourth is intergranular corrosion. Intergranular corrosion appears as a network of corrosion paths along the grain boundaries of the material, often with a rough, irregular surface. The fifth is erosion corrosion. Erosion corrosion appears as a combination of mechanical and metallurgical damage, often with a rough, irregular surface and a mix of ductile and brittle erosion features. Here are some common characteristics of erosion and erosion-corrosion damage from common features of erosion and erosion-corrosion damage point of view, include. The first is surface roughening. Erosion-corrosion damage often leads to surface roughening, which can increase the drag, reduce the efficiency, and enhance the susceptibility to further erosion/corrosion. The second is pitting or craters. Pits or craters are common features of erosion-corrosion damage, often resulting from the removal of material by mechanical or metallurgical mechanisms. The third is grooves or channels. Grooves or channels may form on the surface due to the flow of fluids or gases, which can enhance the erosion/corrosion process. The third is grooves or channels. Grooves or channels may form on the surface due to the flow of fluids or gases, which can enhance the erosion/corrosion process. It's essential to note that the appearance of erosion/corrosion damage can vary depending on the specific conditions, materials, and mechanisms involved. A detailed examination of the damage, combined with a thorough understanding of the underlying mechanisms, is necessary to accurately diagnose and mitigate erosion/corrosion failures. Erosion and erosion-corrosion prevention and mitigation based on API 571. The first is improvements in design involve changes in shape, geometry and material selection. Some examples are, increasing the pipe diameter to decrease velocity, streamlining bends to reduce impingement, increasing the wall thickness, and using replaceable impingement baffles. The second is improved resistance to erosion is usually achieved through increasing substrate hardness using harder alloys, hard facing or surface hardening treatments. Erosion-resistant refractories in cyclones and slide valves have been very successful. The third is erosion-corrosion is best mitigated by using more corrosion-resistant alloys and/or altering the process environment to reduce corrosivity, for example, deaeration, condensate injection or the addition of inhibitors. Resistance is generally not improved through increasing substrate hardness alone. The fourth is heat exchangers utilize impingement plates and occasionally tube ferrules to minimize erosion problems. The fifth is higher molybdenum-containing alloys are used for improved resistance to naphthenic acid corrosion. Erosion and corrosion are critical factors that can lead to significant mechanical and metallurgical failures in various industrial applications. Understanding the prevention and mitigation strategies for these failure mechanisms is essential for maintaining the integrity and longevity of materials and structures. Here's an overview of the approaches for dealing with erosion and erosion-corrosion damage prevention/mitigation strategies. The number one of prevention and mitigation strategies to be considered is material selection. Include, the first is corrosion-resistant materials. Utilize materials with good corrosion resistance, such as stainless steels, nickel alloys, and titanium, which can withstand aggressive environments. The second is erosion-resistant alloys. Select materials that have been engineered for enhanced wear resistance, such as hardened tool steels or composite materials. The number two prevention and mitigation strategies to be considered is coatings and linings. Include, the first is protective coatings. Apply coatings such as epoxy, polyurethane, or specialized anti-corrosion coatings to provide a barrier against corrosive agents. The second is thermal spraying. Techniques like flame spraying or HVOF, high-velocity oxygen fuel, can be used to apply wear-resistant ceramic or metal coatings. The third is lining materials. Use rubber, polyethylene, or other polymer linings in applications prone to erosion to absorb impact and prevent wear. The number three of prevention and mitigation strategies to be considered is design modifications. Include, the first is streamlined design. Optimize fluid flow paths to minimize turbulence and reduce erosion potential in components like pipes, pumps, and valves. The second is avoid sharp edges. Design components without sharp corners and edges where erosion can initiate and propagate. The third is proper slope and drainage. Ensure that surfaces are designed to facilitate proper drainage and avoid pooling of corrosive agents that could exacerbate corrosion. The number four of prevention and mitigation strategies to be considered is environmental control. Include, the first is controlled environment. Maintain operating environments to reduce exposure to corrosive chemicals, such as controlling pH levels, reducing temperature fluctuations, or eliminating moisture. The second is corrosion inhibitors. Introduce chemical inhibitors in fluids to slow down the rate of corrosion. The number five of prevention and mitigation strategies to be considered is operational strategies. Include, the first is regular maintenance. Implement a rigorous inspection and maintenance program to identify early signs of erosion and corrosion to address issues before they lead to failure. The second is monitoring systems. Utilize corrosion and erosion monitoring techniques, such as ultrasonic thickness measurements, to detect wear over time. The number six of prevention and mitigation strategies to be considered is fluid management. Include, the first is control flow velocity. Reduce the velocity of fluid flow in pipes and channels to minimize the impact force leading to erosion. The second is avoid cavitation. Design systems to minimize cavitation, as this phenomenon can lead to significant material erosion. The number seven of prevention and mitigation strategies to be considered is cathodic protection. Electrochemical methods. Employ cathodic protection systems, such as sacrificial anodes or impressed current systems, to protect against corrosion in metals exposed to electrolytic environments. Combating erosion and erosion-corrosion damage requires a multifaceted approach encompassing proper material selection, protective coatings, design considerations, environmental controls, operational strategies, and monitoring. By integrating these strategies, industries can substantially minimize the risk of mechanical and metallurgical failures due to erosion and corrosion, ensuring safety and long-term performance of structures and components. Regular assessments and updates based on technological advancements and changes in operational conditions will also further enhance these prevention and mitigation efforts. Erosion and erosion-corrosion damage mechanisms inspection and monitoring method based on API 571. The first is visual examination of suspected or troublesome areas, as well as UT checks or RT can be used to detect the extent of metal loss. The second is specialized corrosion coupons and online corrosion monitoring. Electrical resistance probes have been used in some applications. The third is infrared scans are used to detect refractory loss on stream. Erosion and erosion-corrosion are significant concerns in various industries, particularly in environments where materials are subjected to fluid flow, solid particle impact, or corrosive substances. To detect and monitor these forms of damage, various inspection and monitoring methods can be employed, focusing on mechanical and metallurgical failure mechanisms. Here are some commonly used inspection methods for erosion and erosion-corrosion damage mechanisms. Number 1 is visual inspection. Include, the first is basic method to identify visible surface damage or wear. The second is can reveal signs of pitting, surface roughness, or changes in color, indicative of corrosion. Number 2 is ultrasonic testing, or UT. Include, the first is utilizes high-frequency sound waves to detect thinning of material and internal discontinuities. The second is effective in measuring wall thickness loss due to erosion and corrosion. Number 3 is eddy current testing. Include, the first is measures changes in electrical conductivity and impedance in conductive materials. The second is suitable for detecting surface and near-surface defects. Number 4 is radiographic testing, or RT. Include, the first is involves X-rays or gamma rays to produce images of internal structure. The second is can expose voids, cracks, and localized erosion effects, dependent on the density changes caused by material loss. Number 5 is magnetic particle testing, or MT. It is used for ferromagnetic materials, detects surface and near-surface defects through the application of magnetic fields. Number 6 is dye penetrant testing, or PT. It involves applying a dye to reveal surface cracks and discontinuities, which can sometimes indicate areas of erosion. Number 7 is Brinell hardness testing. It measures hardness, as erosion and erosion-corrosion can alter the mechanical properties of the material. Here are some commonly used monitoring methods for erosion and erosion-corrosion damage mechanisms. Number 1 is visual monitoring, regular inspections using cameras and drones to facilitate ongoing surveillance in critical areas. Number 2 is thickness measurement, periodic measurement of material thickness using ultrasonic devices to track erosion over time. Number 3 is corrosion monitoring systems, installation of sensors, e.g., corrosion probes, electrochemical sensors, that provide real-time data on corrosion rates and conditions. Number 4 is weight loss coupons, placement of coupons in the environment to measure mass loss over time as a quantifiable metric of corrosion and erosion rates. Number 5 is flow and velocity measurement, monitoring fluid flow characteristics, which can inform about potential erosion areas by understanding local velocities and turbulence. Number 6 is digital imaging and laser scanning. High-resolution imaging and scanning technologies can create detailed maps of surface conditions, enabling identification of erosion patterns. Here are some commonly mechanistic insights of erosion and erosion-corrosion damage mechanisms. Number 1 is mechanical failure mechanisms. Include, the first is erosion typically involves the mechanical removal of material due to high-velocity impacts of particles or irregular flows, leading to fatigue and deformation. The second is erosion-corrosion combines mechanical wear with electrochemical reactions that accelerate material degradation. Number 2 is metallurgical failure mechanisms, include, the first is changes in microstructural properties from both wear and corrosion effects, leading to pitting, stress corrosion cracking, and overall material weakening. The second is consideration of material properties, such as hardness, toughness, is crucial since erosion can exacerbate weaknesses or affect the material's resistance to corrosion. Preventive maintenance through regular inspection and monitoring is crucial in managing erosion and erosion-corrosion damage. By employing various mechanical and metallurgical inspection techniques and integrating advanced monitoring methods, industries can effectively gauge the health of materials, anticipate failures, and take corrective actions to extend the lifespan of their equipment and structures. Thank you.